Section 3.5, Overview of Curve Sketching. We're going to use the details we've been working with in the last two sections about increasing, decreasing, maxes and mins, and inflection points and concavity, those kinds of things, within this section to talk about graphing and sketching curves. One of the benefits in this section is that you do have at your disposal a way to check at least some features of what you're looking with your calculator, right? You can check to make sure that your sketch and the calculator have the basic, same shapes as you're looking at them. Depending on how detailed you want to be, you might be able to find some other details with your calculator as well. So let's talk about first what the important graphical features are. So when it tells you something like identify important graphical features, there are basically 5 features that we're going to be testing and identifying. First one is the domain. So the domain is the x values that you are allowed to have, and you usually decide what x values you're allowed to have based on looking and deciding what x values you're not allowed to have. So things like denominators equal to 0 and negatives underneath square roots. Those are our usual culprits. Okay. Second thing, which we've been working on at different points through the semester, is vertical and horizontal asymptotes. Vertical asymptotes, of course, is when the denominator is 0. And you could throw in slant asymptotes in this case. If you had a case where it was a slant asymptote, it would go into this category. And then the 3 cases for horizontal asymptotes. Remember, if the degree on top is bigger, no horizontal asymptote. If it's exactly 1 bigger, there's a slant asymptote. If the degree on top is smaller, then you've got y equals 0. And if the degrees match, then you look at the leading coefficients. The next feature, and this is where we sort of were able to just eyeball it on the trig problem that we just did, is intercepts. Where does it cross the x-axis, and also where does it cross the y-axis? Because we should be able to plot those points, and it gives some basic form to our graph. All right, so up to this point, 1, 2, and 3 were college algebra things. You knew how to do all of those features in college algebra. There's nothing, and trig if you were working with a trig function. But sections, or parts 4 and 5 down here, these are our truly calculus-related topics. First derivative information. So the first derivative will tell us where our graphs are increasing, decreasing, and where they have maxes and mins. Can I go to the next slide? Are you guys good? It's okay. It's okay. And then the second one is second derivatives. Second derivatives tell us about concavity, where graphs are concave up, concave down, and then also any points of inflection that we might have. That is places where we change from being up and down, up to down, or down to up. So when you're doing these problems, you're going to be finding all of these features. It will help me, it will help the grader, and it will help you if you will just label them 1 through 5. Okay, this is number 1. Step number 1, I'm doing this. Step number 2, I'm doing this, and so forth. Now, there's not always in every graph some of these features. Not every graph has intercepts. Some just don't. Or they may have one type of intercept and not the other. Not every graph has asymptotes. So if you want to get to step 2 and there's not any, you can just say no asymptotes. Just to kind of check off the list. I checked and it doesn't have any. And so as we're working through this, there are some of these places that just don't apply to every single equation that we're dealing with. So let's give it a shot with one. This is a rational function, so it is going to have some asymptotes anyway. We're going to start at the beginning, though, and start with the domain. All right, with the domain, and this is step 1, I'll put it on there too. Remember, the whole goal is to figure out what x can't be. So what can x not be here? 0. X cannot be 0. And we're not writing this down as an answer, because if we, like as an answer to the question, or we would write it in interval notation, but the domain really is all the x's that can't be 0, or that aren't 0. So this is sufficient for having checked this detail. All right? Second detail is about asymptotes. In particular, we're looking for vertical and horizontal, and then slant if we don't have the vertical. So we'll start with, I'm sorry, if we don't have the horizontal. Vertical asymptotes. What is my vertical asymptote going to be? Yeah, but we want to say it as an equation. X equals 0. Right. Okay, the denominator equal to 0 is going to be where I have my vertical asymptote. So that's x equals 0. Now, on this one, we are going to have a horizontal asymptote. How do I know that? By the exponents, right? So tell me what you see here. What is my horizontal asymptote going to be? It's actually 0. Why? Yeah, degree on top smaller. So we've got a horizontal asymptote of y equals 0. Notice I wrote y equals, not just 0. Step 3 is supposed to be finding intercepts. There's two intercepts. There's the x-intercept, or at least for us to try to find. The x-intercept, which is when y equals 0. And you've got the y-intercept, which is when x equals 0. So let's do the second one that I just wrote down first, because what can you tell me about the second one, the y-intercept when x equals 0? Yeah, there's not one here. I cannot let x equal to 0. That is one of the two issues, or that is the issue I wrote in step number 1, right? And then confirmed in step 2 when I was finding asymptotes. However, I can let y equal to 0. Move this one down and give myself a little bit of space. It feels a little bit awkward to write it this way, but I know some of you like to see it actually worked out. This is what we're basically doing. You can multiply by the x cubed and recognize that when you do so, it will go away, right, because it's being multiplied by 0. So if I multiply both sides by x cubed, I end up with 0 equals x minus 4. So what does x equal? 4. So I actually have an x-intercept at x equal 4, y equals 0. So this is an important detail. These are both important details that actually get included on my graph. So far I have 3 important details. And if you want to graph as you go, this would be a good place for us to put those details on the graph. So that's where I'm going to start. I'm going to put those details onto a graph. I think I have space. Well, actually, I have more to do on this page, so I'll go ahead and flip over to here, and we'll put these details on. So I'm supposed to be having a horizontal asymptote at y equal 0 and a vertical asymptote at x equal to 0. And that's my axes, right? Both of those are my x and y axis. So I actually have, dotted lines, if you will, or dashed lines along my axes. And then I also have an intercept here at 4. I'll need this longer in a minute anyway, so I'll make it a little bit longer now. There we go. All right, so far so good? Those are all the details. Now, we encountered this happening before. I remember we talked about it then, but let me just make the comment one more time. It's a little bit awkward. It doesn't happen, all the time, but we do have the graph crossing the asymptote, right? And that sort of feels like you're breaking the rules a little bit, and you are breaking the rules a little bit, but remember, the asymptote behavior is stuff that happens on the ends of the graph, at least horizontal asymptotes. So I can still get close to the ends of the graph without touching it and cross in the middle. And that's what you're seeing happen here. Okay, so we are going to cross the graph, but on the ends of the graph we will get close to those asymptotes. So we'll counter those issues again in a minute. All right, step number 4 had to do with which function? What we're doing on step 4? The derivative, right? Details about maxes and mins and increasing and decreasing and so forth. So we need the derivative, but I'm going to make a suggestion. When you look at this function right here, how could you do the derivative? You can do the quotient rule, and it will work and it's fine, but there's actually an easier way to do it too. So I'm going to suggest that we do this. What I'm going to do is, because the denominator has only one term in it, we could write this way, which you've seen before. We talked about this when we did simple rules of derivatives. It just ends up making it pretty clean. So obviously the x over the x cubed simplifies to x to the 2 in the bottom, or x to the negative 2 on top. and then I can write x to the negative 3 on the second piece. It's a lot easier to take a derivative and a second derivative and a third derivative without keeping doing quotient rules every time. So I'm going to opt for this option for now. Okay? So we're going to take the first derivative of x to the negative 2 minus 4x to the negative 3. So somebody tell me what x to the negative 2's derivative is going to be. Good. And then someone else take me with the derivative for negative 4x to the negative 3rd. What am I going to get? Positive 12. Right. And while we're at it, I'll leave some space and just kind of jump down here. Let's do the second derivative, because that form of this first derivative is the most helpful for finding a second derivative. What would the second derivative be? Good. And what about the second piece? Good. Negative 48x to the negative 5th. All right, is everybody good with those? Okay. So look for ways to make your life easier, all right? Don't just automatically go with exactly the way the problem starts out. If there's a way to simplify it, a legitimate way to simplify, don't go doing things you can't do. If there's a legitimate way to simplify it that's actually correct, that makes the derivatives easier, by all means, use it. I'm actually going to write these with the denominators, or the negative exponents back in the denominator, and we'll look at how we can use this information to find, oops, didn't mean that there, to find where these are equal to 0 then. So this is negative 2 over x cubed plus 12 over x to the 4th. And in order to actually make this helpful for us, we'd like to combine the fractions. And it's not too bad to do so because I just need one more x in the denominator of the first piece. So this is negative 2x plus 12 over x to the 4th equals 0. So obviously the denominator never equals 0. Well, I mean, it does. And then I have an asymptote. We already talked about that. But the numerator also has the ability to equal 0, right? So if you solve this, what will x equal? 6 is correct. Very good. And then I tend to be of the mindset that I like to use number lines. I like to do the testing of points. That's the way I tend to do mine. You could put this x equals 6 into the second derivative and calculate and see what happens there. That'd be okay. But I'm a number line kind of gal, so I'm going to go with this. I need more than just the 6 on my number line, though. Does anybody know what else I need on my number line? A 0. Why do I need a 0 there, Matt?
Because the bottom key equals 0.
Yeah, it's still a critical point, right?
Yeah.
It's not a max or a min, but it is still a critical point, and things can change at critical points. We could have a graph that's increasing and decreasing on either side of the x equals 0 location without x equals 0 actually being a maximum or minimum. All right, so let's test a point before, between, and after. So maybe like negative 1, 1, and, oh, just for fun, 10. Where do we test these points? Good. Into the derivative, you got it. Test points go into the derivative because the derivative tells us where the graph is increasing and decreasing. So we're going to put the negative 1, and we need it into the actual derivative. I'll use this version of it. You can use any version of it you like, but that's one I think that's probably the cleanest. Notice the denominator on this. What can you tell me about that denominator, x to the 4th? Its sign. It's always positive, right? The sign in that denominator is always positive. So do I really need to plug anything into that denominator? No, not really. So I really could just worry about plugging things into the numerator, because that's what's going to change my sign if it changes. So if I plugged in a negative 1 into that numerator, what do I get? Positive or negative? Positive. How about if I plugged in a positive 1? Positive. Positive, okay. And then a 10? Negative. So let's actually identify that this goes uphill, uphill, downhill, right? So what in the world happens at 6? There's a max. So I'm going to have a max at 6. Now, the whole point of what I'm doing, though, is that I want to put this on a graph. So if I've got the max at 6, I need to know what the maximum y value is, right? How do I find that?
Plugging 6 into the original.
Ah, into the original. Very good. So take your original function and plug in 6. In particular, I have 6 minus 4 over 6 cubed. It's going to be a really small number, but let's put it in fractional form. Your calculators will do that for us. What does it give you? Because the decimal doesn't stop and repeat, and it's not nice.
1 divided by 108.
Did anyone else have 1 over 108? Good, I got some nods. All right, great. All right, so we have a maximum at 6, x equals 6, y equals 1 over 108, which is almost 0, right? It's very, very small, 0.00 something, right?
Yeah.
Yeah. All right, so we're at practically 0. So let's actually put that on our graph. Now, it's going to be hard for us to really give a good dimension to this. I'll make my y-axis kind of big in terms of the scale, but it needs to be slightly above the x-axis at 6. So mine's going to look a little bit exaggerated because otherwise you and I won't be able to see it. We just won't. So it looks a little bit exaggerated. It's definitely not to scale, but it is slightly above the x-axis. Okay, is that good? And we know that's a maximum, yes? We also know that the graph is supposed to be increasing before 0. Increasing between 0 and 6, and then decreasing from 6 on. We don't know what the concavity of that looks like, and that actually would change some features of my graph, so I need to do the concavity next. All right? So we'll look at these features next. So I mentioned this is increasing, increasing, decreasing, which we'll put those pieces on in a minute. All right, second derivative. We're going to do the same thing. We want to sort of simplify this, combine it back together, and see what happens. So this is 6 over x to the 4th minus 48 over x to the 5th. And we want that common denominator, so we'll multiply the first fraction by x over x to give me 6x minus 48 over x to the 5th. And this equals 0. There's a lot going on in this problem, right? There's a lot of steps that you have to go through. All right, so we want to set this equal to 0. The denominator will equal 0 when x is 0. Fine. How about the numerator?
X equals
Is everybody good with that? All right, I need another sign chart. So I'm going to use the space over here, and we're going to create one. What values need to go on my sign chart?
0.
0 and 8. Now, in the last example, I told you we could sort of ignore the denominator because it was always positive. Can we do that on this problem? No, because this denominator is not always positive, right? Power of 5, we could actually get something that would be negative in the denominator because it doesn't have an even power. So we're going to use this entire function to figure out what happens with test values. So again, I'll use -1 and 1 because I like those, and I'll use 10. I used it before, might as well again. All right, so somebody take -1 and plug that in for me. Somebody else take a +1. So give me 3 volunteers. Everybody raise a hand. All right, you 3. I got you. All right, Edgar, you put in 1. Matt put in -1. And Tristan put in 10. Okay, I had you put in -1, right? Okay, so Edgar put in -1 for us, and that was negative. Okay. Matt, are you putting in +1 for us? I may have just totally switched who was doing what, but
Yeah.
could you put +1 for us?
Yeah.
What'd you get?
Negative.
Negative. Okay, great. And Tristan? Positive. All right, so this does not tell us about increasing, decreasing. Don't be drawing lines on this sign chart, right? This is about concavity. In particular, I tend to draw parabolas on top of things here. I don't know. Did you do -1?
I did both.
Both. Were they both negative?
No, for -1 I got a positive.
You got a positive.
1 I got a negative.
Okay. You got it fixed then. Is it good? Okay. I'm sorry. I totally confused the issue, guys. Positive. What happens when a graph is positive in terms of the second derivative being positive? Concave up. And I have 2 of those. And what happens when the graph is negative? Down, right, or when the sign chart's negative, I should say. All right, so this is interesting, right? This sign chart looks similar to the sign chart from before. There's a little bit of an overlap, but they both have the interval from 0 to the left, correct? So I know that from 0 to the left, I'm supposed to be concave up and increasing. And I'm supposed to be trapping myself in this graph between these asymptotes. So I have to be either, and I know I don't cross the x-axis because we already tested intercepts and there's not any. I have to be either trapped below the x-axis or above the x-axis. Where am I going to be trapped? Above is correct. And the graph must look something like this. And this is just a sketch, so I'm not really terribly concerned about plotting points. This is a sketch. Curve sketching. So this is what my picture looks like, right? Roughly speaking. Now, what happens between 0 and 4? Because I've got obviously some important feature happening before I cross the x-axis. And actually all the way to 6, to be honest. Whoops. It's increasing, because that's what the first derivative tells me. And what's the second derivative tell me? It's concave down. So I should be increasing. And if I'm close to the y equals 0, or the y-axis, I need to be getting close to the y-axis as the asymptote, because it's an asymptote there. So my graph needs to be doing something. It has to be increasing, which means it has to start below the graph, right? And my graph has to be coming close and cutting through like this. What happens after 6? It's decreasing. In between 6 and 8, what's it doing? Not yet. Concave what until I get to 8? Down. I'm still supposed to be concave down until I get to the value 8. So it still needs to look sort of like parabolic, like this, until I get to 8. What happens from after 8, once I get to 8 and after? It's supposed to switch to concave up. So once I get to 8, and I shouldn't hit the x-axis, it needs to be leveling off and it needs to be concave up. And it's really hard to see that, but if you see if I plot this point here, if I've drawn it well, and if it were a little bit bigger, we could see it better, that it's definitely concave down until you get there, and then it sort of has this very gradual upward turn after that. Is that okay with everybody? Okay. Let's at least start the next one. The next one's not nearly as detailed as this one, but the derivative is so much more fun. Okay. First, domain. What can you tell me about the domain when we're dealing with radicals? What's the issue with radicals and domains? Yeah, the stuff underneath there needs to be greater than or equal to 0. So in particular, the radicand, that's the stuff under the radical, has to be greater than or equal to 0. And if we solve this, we have 2x greater than or equal to 1, or x greater than or equal to 1/2. So on my graph, this means that the graph will not have any values from 1/2 to the left. Flat out will not happen. Okay? So that's step number 1. Step number 2, asymptotes. What can you tell me about asymptotes for this graph? What, Matt?
Doesn't the greater than equal sign, doesn't it change when you divide?
When you divide by negative.
Oh.
Yes, which is good to keep in mind because you may in fact see something you have to divide by a negative. So if you divide or multiply by a negative, you change the direction of the inequality. Tristan?
Is there a reason for these are not finding range? It's not related.
It doesn't end up affecting anything. The range you almost get for free because you get the when you're doing the concavity and the increasing and the decreasing natures. Yeah, so you almost get them for free. If you found it, it wouldn't hurt anything. But you'd be using a lot of the same techniques that you're using in the other pieces. Asymptotes. What's going on this one? When do we get asymptotes? In general, generally speaking. Yeah, when we have fractions or rational functions, when something's divided. Do you have any of that here? No. There aren't any. No asymptotes. Nice. Third one, intercepts. X-intercept, again, is when y equals 0. So let's start with that one. If y equals 0, that's 0 equals the square root of 2x minus 1. what would you do to solve this? Square both sides, which will keep it at 0 on the left, right? And it will simply get rid of the radical on the right. Then what? Add 1 divided by 2. So this would be x equal what? 1/2, that same 1/2 that we got above. So this is x equal 1/2, y equal 0. Thank you. So this will be an ordered pair on my graph. How about y-intercepts? That is x equal to 0. What can you tell me about that? Yeah, this one doesn't exist. There isn't any, or there aren't any, I should say. No x-intercepts. Okay, no y-intercepts, no x equals 0. Sorry. In particular, we're then looking for where the graph is increasing or decreasing. And that's a derivative. So this piece right here, we can write it with a power 1/2. In fact, I think I'll move it there. So what is the derivative of 2x minus 1 to the 1/2? Start with 1/2, right? Pull the 1/2 down, then what? Two x minus 1. What's the new power? Negative 1/2. That is really not a good negative 1/2. Let's try that again. Okay, and then times 2. What can you tell me about the times 2 and such?
Cancel with 1.
Beautiful. So this actually ends up being 1 over square root of 2x minus 1. So think with me. Our goal here at this point in the problems before is to set this equal to 0. What happens? Can't do it, right? I mean, it doesn't equal 0. The numerator is 1, so that stands no chance. If the denominator does equal 0, then it's going to be undefined, not give me 0. But it does have a does not exist value, right? It's when the denominator is 1/2. So in terms of like a sign chart, we can create one. It's just that we'll only have one location on it. In fact, I'll make it like this, and then we'll make a sort of a mention that we can't go on the left-hand side. This location is at 1/2. I can still pick a value over here. I can still find out is the graph increasing or decreasing, but it's not going to have any maxes or mins because whatever it's doing it everywhere that it's on the function. There's nothing over here, right? No values over here, and the values are always to the right of the 1/2. So what happens when I plug in the number 1 into this function? The actual derivative itself that I just created.
Plus or minus 1.
Do you get a positive or negative? No. The square root, is that what you're thinking about? The square root doesn't have a plus or minus on there right now, so we don't put one on ourselves. Yeah, if the square root's already on the problem, then we treat it as though it's a positive automatically. It's called a principal square root. You got a positive? Okay. So what this tells us is that the graph is going to be increasing from 1/2 to the very end of the graph. Okay? So the only last thing left to test is the second derivative for concavity and figure out what's going on with the concavity, if there's any concavity changes. Just because there's not a max or min doesn't necessarily mean there couldn't be a concavity change, so we do have to check and see what's going on with the concavity. Alright, so we'll take the second derivative from this version right here since it's easier to work with and recognize that we have a negative 1/2, 2x minus 1 to the negative 3/2, and then the times derivative inside is 2. The 2 and the 1/2 will cancel, but we do end up with a negative on this one. So we have a negative, and then we have the square root of 2x minus 1, and this is to the power of 3 in the denominator now. And it's a negative 1 in the numerator. So what you'll notice is that this denominator is always positive. If it's 0, it's going to be equal to 0 when x is actually equal to 1/2, the same the number line basically we had before. And we can't, again, go beyond it over here either, just like before. And the denominator is positive because we've got a square root, so it's coming out of a square root is positive, and if you cube something that's positive, it stays positive. So this graph is always going to have a negative, this testing point is always going to be negative when you're bigger than 1/2. So this is actually going to be concave down. So it needs to be increasing and concave down. So if we take a look at our picture, we're going to graph this thing now. We have an intercept at 1/2. It needs to be increasing, so it's going uphill. It's going to be going up into quadrant 1, but in a concave down fashion. And it can't look like it's going to ever actually, hit a maximum and come back down. That's not what it's doing. It's going to continue in this increasing type pattern. If you want, you can mark the y-axis with some scaling units. We didn't really need those features. We're just looking for a sketch, and this will do it for us.